Hello everyone. Today I'm going to present the topic three-dimensional viewing in computer graphics and vision. In this presentation, we will understand how a three-dimensional scene is transformed into the two-dimensional image that we see on a computer screen. We will also learn about the viewing pipeline, coordinate systems, projections, clipping, and visible surface detection, which are the key concepts used in modern graphics systems. These are the topics that we'll be covering in today's presentation. We'll begin with the 3D viewing pipeline, then understand viewing coordinates and different types of projections. After that, we will discuss clipping algorithms, followed by visible surface detection methods like the Z-buffer and Painter's algorithm. Finally, we will compare these techniques and understand where they are used in real-world applications. 3D viewing is important because it creates realistic depth and perspective, making digital environments appear natural. It forms the foundation of applications such as video games, CAD software, virtual reality, and computer-generated films. Three-dimensional viewing has many practical applications. It is used in video games for real-time graphics, virtual reality for immersive experiences, CAD systems, as we discussed earlier, for engineering and architecture, medical imaging for CT and MRI visualizations, flight and driving simulators, and the film industry for creating realistic visual effects and animations. Now, here we have provided an overview of the concepts discussed in the presentation. We will first understand the viewing pipeline, then study the coordinate systems and camera parameters. Next, we will explore projection techniques, clipping algorithms, and visible surface detection methods that ensure only the visible parts of a scene are rendered. Here is the 3D viewing pipeline. The viewing pipeline is the sequence of operation that converts three-dimensional objects into pixels displayed on the screen. It begins with object coordinates, applies modeling and viewing transformations, performs projections and clipping, and finally maps the image to screen coordinates. Every modern graphic system follows this pipeline we have shown in the diagram. Now let's discuss about modeling transformation. Modeling transformation converts an object's local coordinates into world coordinates. This is achieved using translation, rotation, and scaling operations. Each object has its own model matrix, which determines its position, orientation, and size within the virtual world because it is viewed by the camera. Now let's understand about the viewing transformation. Viewing transformation represents the position and orientation of the virtual camera using parameters like the eye position, look at point, and view up vector. The system transforms the entire world so that the camera is located at the origin. This simplifies all further calculations in the graphics pipeline. Now, projection and viewport transformation. Projection transformation converts the three-dimensional scene into a two-dimensional view. Now, perspective projection creates realistic depth while orthographic projection preserves object dimensions. These are the two types of projections we have seen. And after the projection, the viewport transformation maps the normalized coordinates to the actual screen pixels, allowing the final image to be displayed correctly in the device or on the screen. Now, this is the complete 3D viewing pipeline. First, object space is defined, and then TX is modeled. Then, into the world space, we will be doing the viewing transformation. And further on, we'll be doing the projections that we have discussed. And at last, we'll be doing clipping, NTC, and viewport transformations. After that, only the image will be displayed in the screen. Okay, this is the viewport transformation in screen mapping. And as you can see, the formulas of screen mapping for X screen mapping and Y screen mapping, only the X and Y coordinates changes. And but in the brackets, the X NDC, the formula is 3X NDC plus 1. But here in Y screen mapping, the formula has changed. So we have to use these formulas for doing the transformations. Now let's move to viewing coordinates. So before displaying any object on the screen, it passes through several coordinate systems. First, the object is created in object coordinates, then placed in the scene using world coordinates. Next, it is transformed into view coordinates, followed by clip coordinates. After perspective division, it becomes normalized device coordinates. And finally, it is mapped to screen coordinates. This sequence ensures that every object is displayed accurately. In computer graphics, two coordinate systems are commonly used: the right-hand system and the left-handed system. OpenGL uses the right-handed system where the positive z-axis points towards the viewer. DirectX commonly uses the left-handed system where the positive z-axis points away from the viewer. Understanding these coordinate systems is important because they affect how objects are positioned and viewed. Let's move to the next slide. To define the camera in a 3D scene, we use several view reference parameters. The VRP, or view reference point, specifies the camera's position. The VPN, or view plane normal, defines the viewing directions. And the view VUP, or view up vector, determines which direction is considered upward. Finally, the PRT, or projection reference point, which represents the center of projection in perspective viewing. So here we are going to discuss about the view window, clipping planes, and view volume. The view window represents the rectangular region through which the scene is observed. The near and far clipping planes define the visible depth range of the scene. Together with the left, right, top, and bottom boundaries, they form the view volume, also known as the view frustum. Objects outside the region are removed before rendering, which is known as clipping. Now, we are going to discuss about the types of projections. First is parallel projection, projects all objects using parallel projection lines. Unlike perspective projection, the size of the object remains constant regardless of their distance from the camera. There are two main types: orthographic projection, which is commonly used in engineering drawings, and oblique projection, which displays depth while preserving the front face of the object. And the formulas are also given here, as you can see. Now, here we compare the two types of parallel projections. In orthographic projection, the projection rays are perpendicular to the viewing plane, preserving accurate dimensions. And in oblique projection, the rays strike the plane at an angle, creating the illusion of depth. Two popular oblique methods are Cavalier projection and Cabinet projection, which differ in how they scale the depth. Now, perspective projection closely resembles how the human eyes see the world. Objects that are farther away appear smaller, creating a realistic sense of depth, and all the projections lines converge at a single point called the center of projection. This type of projection is widely used in game simulation, films, and virtual reality because it provides a natural looking view. The perspective projection matrix converts 3D coordinates into clip coordinates while preserving the depth information. After applying the matrix, a perspective divide is performed by dividing each coordinate by its WM. This process produces normalized device coordinates, which are later mapped onto the screen. This mathematical operation creates the realistic depth effect seen in the perspective views. As you can see, these are the diagram for perspective projection matrix. Now, the viewing frustum is the three-dimensional region visible to the camera. It has the shape of a truncated pyramid and is bounded by six planes: left, right, top, bottom, near, and far. Only objects inside this frustum are rendered, while objects outside are clipped away. This improves rendering performance and prevents unnecessary calculations. Now let's discuss about clipping. Clipping is the process of removing parts of the object that lie outside the viewing model. It prevents invisible geometry from being rendered and avoids mathematical errors during projection. It also improves graphics performance by reducing the number of objects processed by the GPU. Different clipping algorithms are used depending on whether we are clipping points, line, or poly. The Cohen-Sutherland algorithm is a popular method for clipping lines against a rectangular window. It assigns a 4 unique bit region code called outcode to each endpoint of a line. Using logical AND and OR operation, the algorithm quickly determines whether a line is completely inside or completely outside or partially inside the clipping window. Now, the Lang-Barsky algorithm uses the parametric equation of a line to calculate the exact points where the line enters and exits the clipping window. It performs fewer calculations than Cohen-Sutherland, making it more efficient. Now we will discuss about visible surface detection. When multiple objects overlap in a 3D scene, only the surfaces closest to the viewer should be visible. This challenge is known as the hidden surface problem. Visible surface detection algorithms solve this issue by identifying which surfaces are visible and which are hidden behind the others. These methods are broadly classified into object space methods and image space methods. Now, backface culling is one of the simplest visible surface detection techniques. It removes polygons whose front surface face away from the camera because they cannot be seen by the viewer. This decision is made by comparing the surface normal with the viewing direction. Now let's discuss about the painter's algorithm, which renders objects from the farthest to the nearest, similar to how a painter first paints the background and then the foreground. Although simple, it can fail when objects overlap in complex way. Now let's discuss about scan line visible surface algorithm, which processes the image one horizontal line at a time. For each scanned line, it identifies all the polygons that intersect the line and determines which surface is closest at every pixel. Since it processes one line at a time, it uses less memory than some of the other techniques. The Z-buffer algorithm is the most widely used visible surface detection technique in modern graphics system. It stores the depth value of every pixel in a separate memory called depth buffer. Whenever new pixel is generated, its depth is compared with the stored value. If it's close to the camera, it replaces the previous pixel, otherwise discarded. So in this diagram, we can see how the Z buffer works. Initially, every pixel in the depth buffer is assigned a maximum depth value. As the polygons are rendered, the depth value is compared with the stored depth buffer. And the nearest surface updates both the color buffer and the depth buffer. As a result, hidden objects remain invisible. To conclude, 3D viewing is a fundamental process in computer graphics that transforms 3D objects into realistic 2D images. We explore the viewing pipeline, coordinate system, projection methods, clipping algorithm, and visible surface detection techniques in depth. Together, these concepts form the foundation of applications such as video gaming, virtual reality, and CAD software. Thank you for your attention.